Okay, we're back for the second part of the 6.6 lecture on nuclear power. So we are at the radioactive waste part. So you just watched the video about the Fukushima disaster. And now you're on page 24, and we're going to talk about radioactive waste. So it is high level. Let's do this for you. Sorry. So there's high level and low level, right? So the high level is used in the fuel rods. So you want to write that, the fuel rods. And then the low level is contamination, like tools and rags and things from cleaning. And then there's also the uranium mine tailings. So the stuff that comes off of the uranium mines, just like from the coal mines, the tailings are the things that come off from that. Okay, so these are all negatives of nuclear power. So the high level uranium is used in fuel rods. And after a time, they become spent, like they're used up, they're spent. They can't generate electricity, but they're still radioactive. Okay, so fuel rods is what you're writing on the other little part right here, fuel rods. Okay, and there's Homer. Don't have Homer working in the nuclear power plant. So U-235 has a half-life of 700 million years. So it's around for a long time. So what half-life is, okay, okay, so sorry about that. So what this says here is that sodium-24, okay, so what a half-life is the time it takes for half the sample radioactivity to decay. That's how all radioactive elements work. Half of them go away in a half-life, all right? It's just a physical property of atoms. If they're radioactive, half of it will go away in a half-life. Many radioactive, well, they're really not considered radioactive if they're stable because it takes so long for them to break down. Okay, so we have a couple, and this little guy here, this big guy, you know, this superhero guy, he is half-life. So the little lambda, the Greek letter lambda, represent radioactive decay, and he's a superhero in a video game called Half-Life. And so sodium-24 is a radioactive element, and that takes 15 hours to decay. Carbon-14 is a radioactive element that takes 5,730 years. And I'm sorry, my face is over this. I can't figure out how to get it off. So 5,730 years. And then potassium-40 takes, sorry, it'll go away. Takes 1.26 billion years. Okay, so what that means is it's exponential decay. Okay, so we're going to show that on the next one here. Okay, so as soon as something dies, the carbon-14 starts breaking down in it, and this is how you can tell how long something's been dead. Okay, so the way you would use this, so here's my question for you. So which isotope would be used for figuring out how long a murder victim had been out in a swamp? Okay, so which one of these things? 15 hours, 5,000 years, or 1.2 billion years? Which would be the best one to look at? And the answer would be sodium-24, because it only takes 15 hours to decay. So you could just see, like, if half of it was gone, that means that the person had been dead for 15 hours. All right. And you do a ratio of the radioactive sodium to the non-radioactive sodium. The same for carbon-14. So what about figuring out the age a mammoth had been left behind, how long it's been left behind bones? So that would be carbon-14. And then to figure out how old the rocks are in a meteor crater, like that's not going to be hours or 1,000 years. That's going to be billions of years. So you would use the potassium 40. So this is potassium 40 to figure that out, okay? So when you do carbon dating, if you've heard of that term before, carbon dating means that they're going to look and see how long it takes for the carbon to decay. So the C14 to C12 ratio, because normal carbon is C12, you can figure out how long it's been. So we don't need to do that in particular, but just to understand the idea. So this is how half-life can be used to figure out the rate of decay and the radioactivity left at specific points in time. So you're going to draw this, this kind of radioactive decay idea on your graph right here, okay? Because half, it's exponential. Now, I always like to point out that this is the inverse of doubling time. Half-life is the inverse of doubling time, okay? So you can either double exponentially or half exponentially. So you go from 10 to 5 to 2.5 to 1.25 to 0.625 over a certain amount of half-life. So you have to be given that, and we're going to do some practice with some math. Here's how to do it with a calculator. So you have the final amount equals the initial amount times half to the power of the time divided by the half-life. Okay, so you're going to write that down in the box on your sheet there. Okay, and then you can find out like how much of a dose of radiation you've had, how dangerous it is. So we're going to do a little half-life math, and that the people who are responsible for the names of the units are these guys. So you might see becquerels. So this guy right here is, let's see, I forget his first name. I have it. Anton Becquerel. And then these two are Pierre and Marie Curie. Oops, sorry. So Marie Curie is famous for doing her research on radioactive decay, and these three won the Nobel Prize for Physics in 1903 for their research on radioactivity. So they get the name after them. So with radioactive levels of 100 curies and a half-life of 50 years, what will the radioactivity level be in 200 years? So you can do this by just half, and see how long each half-life is. I'm going to show you the answer. Please try it yourself first, and we'll have some more practice later. So please pause. Give yourself as much time as you need to think. And I'm going to show you the answer. Okay, so this is the answer without using the equation. But you could also use the equation. So I'm going to show you that too. So pause this if you need to. I hate that I'm over this stuff. Okay, so that's good. So you can see that. So you don't necessarily need the equation, but you could do it this way. Okay, so this would be how you would do it using the equation. Either way is fine. Give you enough time to look at that. Okay. Okay, so here's the next one. Next practice problem. There's the answer for that one. Oh, I was supposed to make sure you did it yourself first. Okay, so now let's go back. This picture isn't over it. All right, so where are the fuel rods? So fuel rods are dangerous for 10 or more half-lives, okay? And now where they are, so we have fuel rods from nuclear power plants, and they're stored in pools of water that are shaded from radiation, which is kind of crazy. So this is a little picture of the forbidden swimming pool. So nobody does this. Nobody's actually swimming in a swimming pool, but it's true that the water shields us from the radioactivity. So if you were swimming up here, it's totally safe. If you were down here, you'd be dead in an hour. And if you were all the way down here, you'd be dead in minutes. So it's very dangerous but it's not if you stay far away. So sites have run out of pools, and now they're in lead-lined dry containers on land. And there's Homer and his friends. Don't worry, they're not doing that, but it is just a huge problem. It's very expensive. And remember this idea that if you are going to say how efficient uranium is, it's very efficient because it's so small and lasts for so long. But if you're going to have to pay all this money for the nuclear waste, we haven't found a way to make it worthwhile, because you're having to put all this energy into all these protection layers, right? Okay, so now we get to no waste in space. So why don't we just shoot nuclear waste out of the atmosphere and into the sun? People always want to know. And not just nuclear waste, but all waste. Like, oh, we have too much trash. Oh, we have too much plastic. Why don't we just shoot it out into space? Well, I have to say this so much that a student actually made me a banner that I hang in the room that you guys would be seeing every day. So here's an answer. So it's stupid expensive, it's stupid dangerous if the rocket blows up on the launch pad. At the moment, launching stuff is about 20,000 per kilogram of payload, and that's just get it into orbit. And now there's 270 tons of fuel in storage. So you could do the math. It is crazy expensive. So why don't we just burn it or destroy it or dump it, So most options would allow for the potential of large radioactivity to enter the oceans and atmosphere. So right now we're just storing it. So let me just show you. If you guys were in class, I would make you come and read this over and over and over again, because there's always somebody, you know who you are, that wants to throw waste into space. And I say no. And this is why. We have 3 big reasons. It takes too much energy to send up the waste. Too much energy and money. It's ridiculously expensive, okay? If it blows up, the waste will scatter everywhere. So if the waste is nuclear, then we're just going to have a big nuclear fallout. And then the last one is recycle or die. This is not the right tactic to take. Recycle or die means we need to reuse everything on Earth because we will run out of our resources. So we need to find a way to use this. And there's some cool things going on with ideas about how to reuse waste. And so please don't say that we should put it into space. Okay, now, instead of putting it into space, why don't we bury it under Yucca Mountain? Now, Yucca Mountain is a really important thing that you must learn and memorize, okay? So Yucca Mountain, in 1978, we started a plan to say, let's bury all of the nuclear waste underground at Yucca Mountain. But this, I've been talking about this since I've been there. For 30 years of controversy has led to protests and cancellation of the project. But it is still thought of as a disposal facility, all right? So, but they still haven't passed it. Nobody wants it. And this is a classic NIMBY. NIMBY is N-I-B-Y. You know NIMBY? Not in my backyard. NIMBY. Not in my backyard. People don't want this. So the Nevada people are not voting to have all the nuclear waste come to their facilities or come to their Yucca Mountain. And I just want to point this out. So Yucca Mountain's in Nevada. Look at where most of the nuclear power plants are. Most of them are at East Coast. So you would have to ship all of your nuclear waste to Nevada and bury it under Yucca Mountain. So that hasn't happened. Can you imagine all the transport of that? And then this is to let you guys see where operating nuclear power plants are. And you notice here, California, because you want to know what's near us, right? So this right here is the Diablo Canyon nuclear power plant, and it is in the process of being shut down. We have not built another nuclear power plants since the 1970s because we are so concerned about the problems with nuclear waste. Now, remember, global warming is starting to become, we're realizing what an incredible crisis global warming is, and nuclear power, you can get electricity with no carbon. So it's interesting and controversial to say that nuclear is really good for the environment because it gets you electricity with no emissions. And that is a good argument for nuclear as a transition to perhaps a clean energy future because it's clean for the air, even though there's nuclear waste and the possibilities of radiation damage. Okay, so plans for nuclear in the future. Let's just check back in the lecture notes. Okay. All right, so there's a recent upsurge in applications for new nuclear power plants, and up to 5 new nuclear power plants may come online in the United States in the next decade. So that's going to be really interesting for all of us to think about. Okay, so what you have now is you have 2 videos. Okay, one is Energy Explained, Risk or Opportunity. And then the next one, okay, so you can watch this
nuclear energy and how does it work?
Video.
Since the beginning.
Okay, and then the next video is a silly one on that's from The Simpsons, Nuclear Energy, Our Misunderstood Friend. It's not going right now, but the link is in, is the link in your thing? You could look this up. Nuclear Energy, Our Misunderstood Friend is a YouTube video that, let me see. Here it is. So feel free to look this up. I don't think, yeah, so this is the link right here. And I can try to put that into the lecture for you guys if you want to see it, or you can just look up The Simpsons, Nuclear Energy, Our Misunderstood Friend. And that's all I have for you for finishing off the nuclear unit. Have a great rest of your day.